Good morning to all. So once again, we welcome all to the 5 days FTP sponsored by AICT ATAL program. And so today we have expert Dr. Senthil Kumaran sir from AATM Kanjipuram. He is going to deliver his lecture on 3D printing and Industry 4.0. So let me primarily welcome him for this wonderful 5 days FTP. Welcome you, sir.
Thank you.
Yes. And Chennai Institute of Technology has been conducting a lot of webinars. Almost we have conducted more than 500 webinars from the March once lockdown has been announced. And we have conducted sponsored FTP from AICT and AICT ATAL. And also we have conducted so many self-sponsored workshops. And Chennai Institute of Technology is at the top second position among all other private engineering colleges in Tamil Nadu by the recent results announced by Anna University for November-December 2019. And the Chennai Institute of Technology has been conducting this webinar series named as Knowledge 4.0 under the guidance of the Honorable Chairman C.P. Sriram. And this is being mainly conducted in order to enhance the knowledge of faculty members, researchers, and students as a social responsibility. So let me welcome all once again, and now I welcome Purvasri, the student of first year mechanical engineering, to introduce our today expert. Purva, you can start.
Yes, sir. A pleasant morning to one and all gathered here. This is Purvaja, pursuing first year mechanical at CIT. Today in this session, we have Dr. Senthil Kumaran sir to deliver a speech about 3D printing in Industry 4.0. He is currently working as assistant professor in Department of Mechanical in IIIT DM Kanjipuram. He has completed his PE Mechanical in 2001 at University of Madras and ME in Production of Engineering in 2004 from Anna University. And he has received his PhD in Mechanical Engineering from IIT Delhi in 2009. He has more than 10 years of teaching experience. His specialization includes additive manufacturing, sustainable manufacturing, and smart manufacturing. So far, he has published 20 journal articles in highly reputed journals and has written book chapters too. He is also a member of American Society of Mechanical Engineers and also an editorial member of ASTM Journal of Smart and Sustainable Manufacturing. We welcome you, sir.
So please, you can go to the session, sir.
Yeah, so thank you for the introduction. I hope all the participants are able to hear me and as well as see my screen. So thanks for the introduction, Dr. Prakash. And I think one of the important thing about this online webinars is about understanding the context. Let's say we call this, fourth industrial revolution. So first of all, we need to understand the context, and then we need to understand why this is called a revolution instead of a evolution. And also we need to understand the underlying technologies for the Industry 4.0 and why 3D printing is part of the fourth industrial revolution. So this is the topic of interest, right? I hope all the participants somehow could have known me previously, or if not, you have not attended my session. Some of them may be really new. And some slides I am also reusing from my previous talks to get yourself understand the fundamentals and basics. Okay, so without wasting much time, so I would like to take you through some of the slides. And before that, I would like to, so because there was an introduction about me, but I wanted to give a very quick idea about where do I come from and what we do. So IIIT DM Kanchipuram is an institute of national importance established by the Ministry of Human Resource Development. Right now it's called Ministry of Education, Government of India. So we have been mentored by IIT Madras for 4 years inside IIT Madras, and then we moved to a permanent campus, which is operating at Bangalore to Kalambakkam Road in Chennai. So even though the name Kanchipuram is there, our institute is not related to Kanchipuram anymore now, because now the district is also bifurcated. We are in Chengalpet district right now. Yeah, so we have 14 academic programs on offer, and recently we have introduced some dual degree programs and changed a few programs. And we are the first to basically introduce the smart manufacturing program, which is based on the Industry 4.0 curriculum. So 2016, we started in 2014, and then 2016 we launched the program like 7 years ago. So the first Industry 4.0 eligible graduates have graduated from our campus in 2020, so last year. In spite of the COVID and other things, they got a good, I would say, placements and other things. And also we have situated strategically between IT corridor, that is the OMR road, and the manufacturing hubs. Like we have a very huge automotive hub nearby our place, like Varakadam. We have Ford in Marimal Nagar and BMW and Thiruvattriyur and Ashok Leyland. And so all those companies. So we have been able to basically tap into the IT-enabled design and manufacturing. And we also have IT-focused research in design and manufacturing. We have interdisciplinary groups in cyber-physical systems and smart manufacturing. So this is our basic introduction to our institute. So what we do in our institute, so what is my roles in this institute, like in research, I run a laboratory called Design for Additive Manufacturing Laboratory. And we also run a smart manufacturing programs, UG as well as PG programs. And also I am the research head of smart manufacturing division. So, and also I'm the coordinator for a teaching learning center, so which conducts a lot of training programs in 3D printing, robotics, so that you can build your own 3D printing, you can build your own CNC machines, and typically like micro dispensing. So lots of edtech development happens in that particular place. It's an outreach activity, which is also funded by Ministry of Human Resource Development. And then now it's called the Ministry of Education. Okay, so I think this is about what we do and where I come from, right? So, so I just wanted to start off with some commercial things before I go into the research aspects of additive manufacturing, because additive manufacturing is largely driven by research, and then we have a lot of commercial activity that has recently taken place. If I look at this is the research areas, I think I can show you here. I think you can see my cursor is moving there. So this is the design area, so where we have lots of research going in, AM. So before I begin, I want to give quickly the nomenclature. So we usually call 3D printing by many different names depending upon where the context is being used. Let's say if you are making a prototype out of the process, then 3D printing, then we usually call them as rapid prototyping. And suppose if you are using it for tooling, we call them as rapid tooling. Suppose the part out of the 3D printing. Suppose if that is going to be used, plastic parts are going to be used as an end product, then we call them as rapid manufacturing. And if your design is so complex and it's free-form, we call them a solid free-form fabrication. In all the 3D printing process, we use layer by layer technique. So it's also called as layered manufacturing. And in addition, we also have other names like additive manufacturing, which means like we are adding one layer at a time. So the others is a subtractive and forming and other types of manufacturing processes of that. So this is typically additive process. So there are 50-60 odd processes which comes under 3D printing, and they are grouped under 7 classes. Recently, ASTM came up with their classification. So what happens is like, let us say you have a laser beam which fuses powder particles on a pre-laid powder bed. So typically these are called powder bed fusion techniques, right? So suppose if the same laser beam is used to monomerize a photopolymer, then they are called vat photopolymerization, because the liquid, the starting material is in the form of a liquid and which is contained in a vat, and then that liquid gets selectively photopolymerized upon exposure to a laser light. So that is called a vat photopolymerization process. Okay, so yeah, so so if I look at that classifications, we have further classifications based on whether you are using a binder to glue the particle rather than a laser, then it's called binder jetting. Suppose instead of a binder, you use the material directly to jet it, like an inkjet printer. So if you use some other resins to jet it and then print layer by layer, then it's called material jetting. And we have further process. Suppose if your starting material is a sheet stock, right? So instead of, let's say, a powder or a liquid, or let's say, so if you start with some sheets and then you laminate them together, so it's called sheet lamination. So either you can laminate them by using, let's say, a binder, or you can also weld them, micro weld them together by either using ultrasonic consolidation and other kinds of processes. So you can take a sheet metal and also do the metal thing. Right? So in binder jetting, typically you can also use metals. So recently it has become very famous now. So I'll talk about it a little later. Okay, so now you have seen vat photopolymerization, we have seen powder bed fusion, we have seen material jetting, we have seen binder jetting, and we also have sheet lamination. And now one more process which has been adopted from cladding, which is not usually used for printing parts, but rather for repairing and kind of building near net shapes. It's called a direct energy deposition process. So these are some of the 7 classifications of additive manufacturing. And recently there is a process for making electronics which are called direct writing, which came into being. Now, if I look at the electronics portion here, so these electronics things are typically called as direct writing, right? So whereas Optomake works on aerosol jet, whereas Nanodimension works on inkjet, whereas Nanotech works on typically called as this quill type, and then you have other printing process which are based on so nozzle type. So nozzle, quill, and ink, as well as aerosol are typical direct writing techniques, which comes under the 8th classification. They are typically used to produce functionally integrated electronics onto the mechanical parts. So for IoT and Industry 4.0 applications, I will talk about it a little later when I do the functional integration part when I discuss them. Okay, so then we have polymers and metals, which are typically there, polymer machines and metal machines. The polymer machines are typically ideally used for end products for manufacturing as well as for rapid prototyping. Sometimes they're also used in tooling, jigs, fixtures, and also they are used in medical in large numbers for scaffolds and bioregenerations, and then also for tissue printing, they use biomaterials and things like this. So it's got medical applications, it has got aerospace applications largely. So these are the 2 major industries which largely benefits. And looking at the software windows, software vendors, you can see there are a lot of designs which has recently come. That's what I was talking about. So I'll talk about a design a little deeper, right? So also there are simulation softwares. Like previously there were no tools available for 3D printing and additive manufacturing to verify the process. Like in CNC, you would have seen like tool path verification is being done before you actually make the part, and then also in metal forming they do simulations to check whether forming limit diagrams to see whether there are wrinkles. In casting, you will use simulations to check whether there are any blowholes or porosities or even some other defects like misrun and things. So in 3D printing, there are many issues, like we'll discuss one by one a little later, like delamination, porosity, cracking, and then you have things like what we call as this distortion, and then we also have surface roughness and things like that. So we need to basically simulate the additive manufacturing process using some of the software, right? So what we call here all these softwares are typically proving grounds. Like before you actually make a part, in order to reduce your iterations, you can set up a model inside simulation software and run a physics or first principle based simulation and get a first-hand feedback on the quality of the part. So and also check the conformance to the specifications. And if it's not, then you can actually play with the process window or process parameter, or in fact completely redesign the part. So these are some simulations that are commercially available. So a lot of things are coming from the universities. So if I look at all these major metal machines as well as polymer machines, they are all from research institutions. Like for example, Optomake came from Sandia National Laboratories, and for example, so Desktop Metal came from MIT. So 3D Systems also is like independent company. So Markforged again came from a university, right? So for example, the machines like Exxon, which is a binder jet which came from a university. So G Additive has occurred Arcan, which came from Sweden, right? So and things like that. So you can see other Instech is from a Korean university, so which is a joint industry venture and things like that. So you can see that many of them came from universities. So the professors patented this process and then licensed to a company. So these companies must have licensed most of these things from a university. So majority of the contributions for research for these companies has come from universities. So that's why. So what they do is they develop a new process. So there is a process research. I discussed few processes. There are other processes which have been developed and then they become obsolete. For example, there's a process called solid ground curing. So the solid ground curing processes are obsolete now. So there's a company called Kiviton, so which was in Israel. So now this company has become, kind of, so they became obsolete now. So they are away from the market. The company closed down. So those things are there. And there's a process called ballistic particle manufacturing. So also that process didn't really kick off well. So in fact, there's a very good process called SDM. Shape deposition manufacturing came from the university, which is I think Stanford, right? I think it came from Stanford, so it didn't kick off very well. So there are failure stories and there are success stories in terms of how you basically take this research into commercialization and then patenting and then also ultimately licensing and making machines and selling machines and making money, right? So these are and there are also workflow softwares like for example, this is a German startup called 3YourMind. So what 3YourMind does is like you must be knowing that many companies are now beginning to move towards 3D printing. So they have been making parts conventionally. Now they want to explore 3D printing. So but they don't have an idea about how their design could be suitable for 3D printing or not. So you can upload your CAD model or 3D design and then you can get a visual feedback in a, let's say a bubble chart or a simple scatter plot, where in one axis you put a viability and another axis you put technical feasibility to check whether your existing designs can fit into the space, and then try to redesign and move it to the higher return of investment kind of thing. So those things are like workflow, and workflow softwares can also take care of the entire process chain. So for example, the process chain in 3D printing is not that easy. So like for example, in a Word document, you type something in a Word and then you say file print, so you get a printout very quickly. But in 3D printing, it's not that simple. So you need to build the part. So you cannot just say part, go to menu, say part build. It won't be built. So you have to do a lot of things. Like first you have to model a CAD design. Right? So that has to be exported in a format called STL file. Eventually, what you are trying to do is to basically degrade the quality of the model to take a very good model and then tessellate it and get it into approximate model called STL file, standard tessellation language or serial lithography file, right? So this is a one file format which has become a de facto standard. And recently there has been a lot of new file formats which has developed, but STL still remains the favorite one among all the machine manufacturers as well as people in the printing. And if you look at, there are other polymer machines. The polymer machines are like, as I said, these are commercial machines, and I think there are some process which I haven't told you. Like there's one process called material extrusion. So this process is like it uses a filament and it extrudes the filament to form layer by layer parts. So this process, the patent expired very long ago. So then the enthusiast community, so we call this as the hobbyists, right? So they took and built open source printers. The first one being RepRap, which is called replicating rapid prototyping, which means like you can take a 3D printer. You can build another 3D printer with another 3D printer. It's like if you buy one 3D printer, you can make multiple 3D printers out of it. So that's why it's called replicating machines. So that was the first open source build, and then it actually became a wildfire, and many universities started building open source machines, right? So now what is happening here in this hobby space is like mostly the material extrusion process, which is like very cheap. Now you can go to Amazon.com. or Amazon.in, so you can buy a machine for 14,000 rupees. So not more than that. So the filaments, you get something like 2 kg or 3 kg filament for 1,700 rupees. And you can make parts like, let's say, make some 100 parts out of one filament spool. So that means it has become extremely cheap. So the open source movement has democratized. So all these commercial players still, they sell the machines, but still, the desktop machines, what we call here. So they are very small footprint. They work on extrusion, material extrusion type of principle, and they are very cheap. The Chinese has made so cheap that it's becoming, a hobbyist thing. So now the schools have started buying it. The colleges have started buying in bulk. So they are replacing the first year workshop course with 3D printers, so that they can actually, instead of filing and other things, they do a solid modeling and get the 3D model they want. And also there's a vibrant online community. So there's a website called probably you must have come across called shapeways.com, and also Thingiverse. So these are places where people exchange their ideas, their designs, their CAD models. And in fact, they kind of offer them as services. So you can actually choose a machine and build your parts from a machine. So if you have a machine, then you can just servitize that over the website. So so these are things that are happening. So I just wanted to give you an overall, informative view about the existing things. And also you have material suppliers for polymer materials and metal materials. So earlier the material used to get supplied along with the machines. So it's bundled usually. Sometimes when you use materials from other vendors, it may not work really well. So for example, the machine that I worked 16, 17 years ago, it's a UIS machine. So my PhD is on UIS machines. So I started working on polymer machines in 2003. So I think almost close to 16 years ago. So that time, I think we didn't have any other material suppliers. So we had to buy the materials from them. So let's say a polyamide material may cost something like 70 euros. A titanium material may cost something close to 440 euros. Now I think the material cost has drastically come down. The competition has increased, and there are other players who started making these materials, right? So, and these are some. So I think 3D printing is becoming more versatile. Earlier, we had material choice. Yeah, I'm hearing some noise.
You are on which slide, sir? Slide.
So I'm still on the AI ecosystem.
Fine, sir. Fine, sir.
Yeah, so
AI ecosystem. Fine, sir. Fine, sir.
Yeah, so these are the things that I want to
please go ahead,
about the AM ecosystem. So and if I look at the AM ecosystem, as I said, design research is predominantly by design, and materials is developing new materials and characterizing new materials. Like as I said, new materials are being constantly under development. So polymers, metals, and ceramics, and all those things. And science is typically about understanding and building simulation models. So maybe you have there's a lot of physical phenomena that happens. Let's say if you take a simple product diffusion process, so where you have you call this processes as the kind of heat transfer type of process, where you have a heat from the laser is being used to fuse the product particles together, melt them, right? So then you have absorptivity, conduction, and then convection, and radiation, and melting, and sensible heating, sensible cooling, right? So, and then you have the melt flow dynamics. The flow is happening there. So you need to construct some engineering FEM simulations or numerical simulations in general, right? So, or maybe data-driven simulations to predict the behavior during this physics. So that's typically science. And in fact, we have my research group largely works on design, and we have done few works on materials and process science. For example, we have developed some few electrohydrodynamic based processes, and we are also developing micro dispensing based new additive process. In fact, materials we are working with nickel alloys. So we are working on Inconel 625 and other things for aerospace applications. So we are not working on medical applications as such. Science, we have built data-driven predictions. We build surrogate models to predict the distortion and warpage in polymer fusions. So, but we also work on design. So I'm going to talk a large number of slides on design. So I'm not going to focus my attention on any of these things. Okay, so this is about additive manufacturing. I told about my institute, and then I told about so what I do, and then I told about in general what the world is doing and what are the commercial things and what the universities are doing, and then what the research ecosystem is and what the commercial ecosystem is. Now, so we are changing gears. I want to tell you a bit about fourth industrial revolution, and then go back to additive manufacturing and design for additive manufacturing in detail. Okay, so now I think I should read this quote, which I use largely in many lectures, which is called adapt or perish. So now as ever is nature's inexorable imperative. So what H.G. Wells tells us in this quote is like, if you're not adapting to changing market conditions and changing technology, so we may doomed. For example, when we studied, we had a planar and a shaper, which are typically non-rotating workpiece and non-rotating tools. So which comes into the group 4 category of machine tools. Now they are extinct, I would say, because none of the workshops have. So for example, the planners, they still have the planners, and if they are not adapting to the new modern technology like CNCs and turn mill centers and CNC controlled farming equipments. So you see this guy is sleeping here, so because he is not able to adapt, and he has lost all the jobs because he has not modernized his plant, and he has not looked at capacity building or moving to what the industry needs. So that means as a teachers, we also have a important role. I think most of us who are joining here may be teachers, not from an industry, but the industry drives us, making our syllabuses and things like this. So suppose in your manufacturing course, if you're still teaching forming, let's say, or maybe just a planner and shaper, probably you are preparing someone for nowhere. So you may not get a job somewhere. So we need to look at, job growth. We are not looking at something like unskilled people, but right. So high labor-oriented people. Right now, people are able to basically becoming more nimble. So they need to have very advanced training and skills that will give them the competitive advantage, right? So that is what the advantage of Industry 4.0 is. Fourth Industrial Revolution is about adapting to technologies which actually bridges, many different disciplines together. So it's not silos anymore like we have in mechanical. Now you take any automobile or a car, right? Electric car. So 80% is electronics now. So you don't have a driver, and in fact you don't have an IC engine at all. So you don't have a piston. So you don't have a emission norms, Euro norms and all. They are going to become obsolete when the engine is not there. So it is extremely important for us to basically change our curriculum and then rediscover the way we teach our students, and then keep our programs updated, and also make sure that the people who we are working with, they are very young minds. So we may have to basically train them to become the 21st century workforce. So that we call them Generation Alpha, right? So generation. We had a Gen X and then Gen Y. Gen Z is what we are training, and then Gen Alpha is coming. So they are becoming increasingly connected together, and then they're using mobile phones. 5G network is going to come, and then they're going to be data generating generation. We call them Alpha generation, right? So, and this is because of the performances. As I said, the factory assets have become extremely important to be competitive, right? So it's become globally competitive. Chinese manufacturers are becoming, extremely redundant right now because of the COVID and other situations, right? So it becomes imperative for them to basically adopt fast-changing fields and things like that. So these are some of the challenges. And also the people are looking at extremely lower cost and higher quality products at a reasonable time for them to develop and launch into the market, right? So the Chinese people are doing that extremely good, and then we have to also catch it up with them, right? So the capital and operating cost needs to be lowered. So Industry 4.0 actually helps many industries. So now if you see if I put them in a 4 quadrant, so there are high potential industries, right? So they could be employed with the Industry 4.0 technologies, but they are positioned well for the future. And there are strong current bases, but they are very leading industries like GE and Siemens and Bosch. So these companies, they are first movers. So they're adopting fourth industrial revolution technology very quickly into the manufacturing shop floors and the production process, in the life cycle, in the supply chain. So they are able to basically come up with really good amount of knowledge and skills and know-how and patents and technologies, so that they can sell it to the worldwide market, right? So they can export it to India and things like this. So we are also trying to do a lot of things, but still we are at legacy systems. We are at very risk for the future because we have a very strong current base, but the problem is we are only with the legacy systems. We are still trying to understand the micro aspects of manufacturing process. We are ready to adapt into some of the things that actually is needed to be adapted, right? So, and this is called the capability maturity model. So to understand how industries are positioned. So I quickly tell you about what is happening around the world in fourth industrial revolution. So for example, look at manufacturing. So when I was working at NIST, which is called National Institute of Standard Technology, around 2012 and 13 timeframe. So that is when the Industry 4.0 document was released by German government. So it is spelled in a different way. It's called INDUSTRIE, so industry, because it's a German-driven thing. So the German Chancellor Angela Merkel announced the policy. It's a German government policy to basically adopt a few technologies and then reach a convergence, so that they can achieve very high productivity and very low cost of operatings, and then also very high skilled labor can be done. So that's what they wanted basically. The major reason or the motivation for them to work on such a fourth industrial revolution because is that they have a very aging population. So that means that they had a huge population who are actually somewhere around 60s and 70s. They're not ready to work for the factories. So they have very high labor shortages. So they wanted very high automation in these factories. Whereas countries like India, we have a very young population. Our demographics are very young. So we have a huge number of people who are jobless. We need, we need to get them into the job. But the problem is with the low skill job that we are generating, like Ubers, like Olas, and like we have this Swiggy's, Zomatos. So they are very low skilled, right? So, but we need to generate very high skilled jobs, because highly labor oriented, low skilled jobs are not going to stay for long, right? So suppose if you have a knowledge economy, so the knowledge can be always useful, and the money generated can be extremely high, and the country can prosper. So that's why many countries doesn't want to basically use the laborers in an unskilled way. So they want to create very high skilled jobs so that they can even export. So India, whether this is applicable or this question has been asked for many times. So I would like to say that Indian industries needs to invent and then develop 4.0 and sell it to the countries where there's a demographical problem. Like China is also facing the same issue, because of one-child policy now. They are also facing labor shortage in the markets and things like that. So many European countries, like Italy, would have seen a lot of COVID morbidity just because of because of the aging population, right? So that is one thing. So we have to make a lot of things in India and then export it to those companies. Like US, they have done they have made some innovation institutes in response to Germany's Industry 4.0, and one of them is smart manufacturing. So, and this is for power electronics manufacturing, this is for composites manufacturing, and photonics for lasers and things, and flexible hybrid electronics, and then smart manufacturing and clean energy is one. And then this is NAMI, this is 3D Printing Institute, which is the first one which formed, which is there in Ohio, right? So, and you also have digital manufacturing, which is also part of the fourth industrial revolution. So this is what is happening in European Union. If you look at very closely, you have multiple countries having multiple programs to do that. So the German one started first, which is called the Industry 4.0. So we are talking about it today because 10 years ago, so in 2011, German government came up with this policy document. Now it has become a standard document. Many standard agencies also took this Industry 4.0 philosophy and applied, and then they generated variations of this multiple platform technologies. It's called platform because it's a platform of technologies. So these are some of the other countries, like European Union in general, and individually countries have things like separate things, like for example, demo law and production 2030, made in Denmark, and smart industry, Holland and things like that. So you have a lot of things happening there. So we call this as manufacturing renaissance because I think there are some technologies which are called evolutionary because they take 30 years of time to grow. For example, computers. So the first computer was built in 1960. And so now we have every home, I think, has at least 3 computers right now, as of now. So on average, so people have 3 computing devices in a home. So some homes don't have a computer, but still, like on an average, if I look at, so 3 computers is that I'm considering the mobile as a computing devices. So so that is the growth. Like it has taken something like 60 years. It has evolved. But whereas some technologies are revolutionary, that means they progress at a much faster speed and faster adoption. Like 3D printing, 30 years ago it was invented. Now if I look at US, so every household wants to have one 3D printer in the home, and they want to personalize the manufacturing and make it distributed way instead of making something in China and then shipping it and storing it in warehouses and distributing through logistics into retail stores, right? So into the customers. So what they want to do is they want to make their own parts in their backyard. So that has become one revolution in US. That's why it's called revolutionary, not evolutionary technology. So India is also doing a bit in Make in India and other things. But the problem with India is like our manufacturing industry is extremely diverse. So we have like the people who are making in a small scale and extremely manual and laborious things like leather industry and cottage industries like potteries and things. And we also have moderate SMEs, like we have manual assemblies, and like Ford and BMW is completely manual. So what we do here, so this is completely automated in Pune, Chak and GE plant. So and this is like an Ambattur plant which is there. So a lot of things are happening in India. So but the problem is whether Industry 4.0 can be applied in all the industries in India. It's not going to be a viable solution. So we need some places to start somewhere in first industrial revolution itself. So then slowly move to second industrial revolution, and then some places it's not even IT automated. So third industrial revolution, and then come to fourth industrial revolution. So we have all the industrial revolution need to reach. For example, this guy is still not having any motorized thing. The mechanization has to happen in some places, right? So mechanization even has not yet happened. So that's the kind of thing. So that is the first industrial revolution, right? So the mechanization. And some places like this, they don't use any transfer lines and automation. So it's still craft production. So that has to move into transfer line. That is the second industrial revolution, right? So, and these places there are not much IT that is there. Even though they have automated, they have programmable automation like CNC machines there, but still they don't have IT automation. So that will take some time, around third industrial revolution. And these factories are completely automated, but still they have not done robotics and things. It is fourth industrial revolution. So collaborative robotics and applying big data and also using some other technologies like additive manufacturing. So which would take another generation for them to move to fourth industrial revolution. So this is the Indian story. So what is the world today? As I said, it is increasingly connected. So now these are the platform technologies which is identified by Industry 4.0 document, and recently there has been additions like cyber security was added very recently. Now it has become 11 technologies. So initially started the Industry 4.0 started with a few technologies, and then later they have expanded it to even 3 or 4 more technologies, which has recently come up. Right, so Internet of Things, I think many of you might be knowing what is IoT. I don't have to go in detail into all these technologies, platform technologies, what we call as. So whereas smart manufacturing or Industry 4.0 is nothing but the convergence of all these technologies. Like advanced simulation is, so I'll tell the characteristics of this. So what happens is like, there's a business driver. If I look at the adoption of Industry 4.0 in industries, because of there is a plant-wide visibility and automation that is to be happening, and there's also there should be a shift from proactive to predictive maintenance. So what is happening currently in most of the industries is like they are using reactive maintenance strategies. So which is like don't fix it until it's broke. So it's the policy that they follow. Now what is happening is like now you are able to instrument some sensors and then collect some data and transmit it over network and then put it in the cloud and then use some analytical services and then carry out some data analytics and then get a meaningful actionable intelligence from the data and then use your wisdom and then drive your production performance. So that's the kind of thing that what Industry 4.0 envisions, right? So now that is the reason why people are trying to basically shift from maintenance strategies. So that is one. Another one is like, there's a lot of disruptions that are happening in the plant. For example, it may be coming from internal, probably there is some machine fails and some machines goes out of service, and there are external. For example, suddenly the regulations change. Like they say you have been using lead for the soldering. Suddenly they say like lead is carcinogenic, and there's a regulation called RoHS, restriction of hazardous substances. There's another regulation called REACH, registration, evaluation, analysis of chemical substances, hazardous substances. So those regulations calls for complete elimination of lead. So then you have to reinvent the process. So that becomes another disruption. So, and also Euro norms, like suddenly Euro 1, Euro 2, Euro 3, and then suddenly Bharat stage 4, stage 6. So these things you have to reinvent constantly because of the external changes. And other things are also happening, like flood. Chennai is always flooding, and then 3 months no production. And sometimes there's, cyclones. Recently we had 2-3 cyclones visiting Chennai and the neighborhood of Chennai very recently. So a lot of automotive companies are getting disrupted because of people are not able to go. And in fact, there's a big disruption in 2020 is COVID. So that's a problem. So you have, then there are some critical orders are also there. Sometimes you need to suddenly make thousands of ventilators, and automotive companies are asked to do it. So in US and in India, so you have to critically handle some critical orders. Suddenly there may be a need to produce something. So they invoke the Defense Manufacturing Act and ask in US, and all the automobile companies are now put to make medical equipments, the personal protective equipments, and things like that. So that becomes like very challenging for them. And also even the same cars and components, sometimes the orders can be very critical, sometimes it will be very low, demand can be extremely high. So you have to be agile enough. So the agile manufacturing philosophies have been there, but in Industry 4.0, so you are able to basically collect the data and predict the performances and predict the understanding of the process so that you can be able to put this data into use. That's what we call the plant information to work, so that you can operate the plant at peak energy efficiency because of the sustainability and other standards. And also right now you have a lot of things available over cloud. So earlier you need to basically have many things in-house. Now you can do many things through cloud-based app ecosystem. So a lot of things can be servitized through cloud. So either in platform as a service or infrastructure as a service or software as a service or your machine as a service, things like that. So Yeah, so this slide is where I'm going to explain you about the connection between 3D printing and Industry 4.0. So what is the connection between 3D printing and why it is becoming so important technology in 3D printing? So now let's, this particular thing, I have been talking about this for a while in many talks, and I'll try to explain it here in a very detailed way. So 1850s, as I was talking about, the first industrial revolution was there, about mechanization. People are trying to basically make craft productions. So they have been making cars, and they have been making ships, they have been making planes. So what they have been doing in the 1850 to 1900s is like, initially they have been making it in a craft stage. So it's like, you build a product, one piece product. So then when the Ford Model T was launched, so it was the first car to be mass produced. So what is mass production? I think mass production, you all know. It is about having a very high volume. Volume means like number of cars getting produced, or the quantity, you can say. So very high volume manufacturing. So how do they achieve the volume? Is through transfer lines. They may have a moving transfer line. So the line will be moving, and the workers has to assemble extremely fast, and so that the product comes out. So in 7 minutes, a car can be manufactured. The total cycle time that is there in the assembly shop, right? So, and that eliminated the need for craft production and things like that. But the problem is they've been using a lot of dies. Like, let's say they've been using stamping dies, which is extremely expensive, and the cost of the die is extremely high. So until you make thousands and thousands of parts of the same design, so your cost cannot be recovered. So meaning that you have to basically make thousands of components so that you can amortize that cost of the mold or a die or a jig or a fixture, like tooling. So we generally call them in the name of tooling. So the tooling is a very important activity. Either you take it machining or forming or casting, you have to make patterns and then molds. And if it's injection molding, you have to make an injection mold. Die casting means you have to make a mold. So you see that these conventional processes which are ideally used in automotive, even stamping, you need to make a mold, die, right? So these are making a die for a very complex shape is extremely expensive. So they used to have at least good number of parts to be produced out of it. So to make sure that the cost of the die gets amortized over its volume. So that became like making one car, the same type of car. That is what we call as mass manufacturing. So you see here, so the mass manufacturing is about higher volume, right? So this is from manufacturing a very few component. In the second industrial revolution, we moved to mass manufacturing, right? So now, so the people's preferences have changed. Now people want actually customized. Now imagine that you are taking someone from your family. Maybe let's say you are a male, you are taking your wife to a store, or probably you are a female, you are taking your husband to a store, right? So let's just take a female for example. So you go to a shop and every saree is of the same kind. So would you be buying a saree? So I don't know. So everybody wants to see different designs, and the person who is there in the stores, until he became tired, like he has to display some thousands of styles until you see one saree design that suits you really well, and you don't have, and also your neighbors don't have, and also your office people don't have. So you need to basically buy one saree. For that, I personally have good experience of having patience and waiting for those period of time. I sometimes I pity around those people who are in the like counters who are displaying these designs and then getting tired. I'm seeing them. I empathize with them. So sometimes So, but that is the like what we call this as customized for the individual. So people want their designs to be customized. Like say you take a bicycle. So people have different heights. So they want to have bicycles to be customized. So you need to have height adjustable stands, and seats can be a little larger in size and smaller in size, and the handlebars distance between them. So you need to customize many things. So that is one. So even you take a lot of other things, like earlier people are stitching together. The tailoring is like the word tailor-made or customization even comes from the stitching, right? So we need to make something that suits a particular persona. So that is becoming extremely important now, because like you take any car. So there is a Audi car builder is there. That is called build and price model. So there is another thing. So people have been like trying to move from mass production to something called mass customization. So what is mass customization? I will tell you. So when you are customizing a product for the individual, right? So the cost will be extremely high. Let's say you are making a die cast, right? So, and you are making each design one mold. Let's say you have 10 different designs. So instead of, let's say now the design, let's say 70, 80 lakhs is what the cost of the die is. And if you're selling, you are throwing away the die after making a part, that 70 lakhs should go to the car. So a basic Tata Nano car cannot be sold at that price, because the dies which are used to make the door trims, or probably the engine trim, or the trike trims, or even the body in white, other assemblies that you do, until if you are throwing away those things for just one design, the cost is never justifiable, right? So that means if you are customizing, if you are changing the design or a color or shapes for individual preference, right? So that becomes extremely expensive. Now, what is mass customization? Is about having very high volume and also very high customization. Is it possible? Now, another definition for mass customization is you make large variations in design, at the same time remain the same cost as the mass produced one. Is it possible? So additive manufacturing or 3D printing makes it possible because it eliminates the die. So that's why it's called a die-less manufacturing or a net shape manufacturing, because you eliminate the complete die. So in one single build in a powder bed fusion process, you can make 100 different variations or even more than that if it can fit into the platform, and depending upon the size of the parts that you are making. So I will show you some examples of mass customization and case studies as I move along. So now after 2000, the industries have moved on to globalization, so where you can buy one part from here, and the interchangeability was always there during the World War. So what happened is, like, the people discovered that they need to replace parts from many countries, so they have to make it at multiple factories and assemble them together. So they standardized and made interchangeable. But the problem is, again, globalization has led to variations in the way that you drive. For example, you make a right-hand drive and left-hand drive. So those things are really different in different countries. So you have to personalize and you have to also globalize. And regionalization is about, again, you take the product, you have to sell it into the world market, but at the same time, you have to customize the individual markets. So you have to put the seats in right in some countries, you have to put the driver seat in left in some countries. So it depends upon that. So, and also the products have become extremely complex now. Previously, it has become so simple. Just take an example of a mobile phone. Now it has replaced hundreds of devices. It can do multitasking because of the app ecosystem. So it has become so complex now. So it is having multiple functions, and then so also it is getting personalized. And the problem is now we want to manufacture them not in one place. Like, they want to attack the Chinese dominance, and also they want to manufacture it in their own backyards, right? So they want to decentralize the production. So centralized factory production is becoming a concept which is becoming obsolete. So the industry 4.0 aims for these kinds of activities. Like, they want to do decentralization, distributed manufacturing, and also they want to personalize the products, and also the products are becoming extremely complex. So that complexity is what this axis is. I think maybe you are able to see here, this complexity is the products are becoming increasingly complex. So I'm going to define some 4 complexities in my lecture. So we have a shape complexity, we have a material complexity, we have a hierarchical complexity, and also we have functional complexity. So in addition, we are also working on complexity. We have also identified even 7 more complexities in design that are increasingly becoming possible in additive manufacturing, which is not possible in conventional manufacturing. So we'll just talk about those opportunities that exist within additive manufacturing. So now this is the complete manufacturing freedom, where you can hit the volume, hit the variety, and also hit the highest complexity. So that comes from additive manufacturing. So that is why additive manufacturing has become a part of industry 4.0. But it has got its own challenges. In title I told I'm going to discuss about design opportunities and also challenges. I'm going to tell about the challenges towards the end. So this is the one that I was trying to explain. So as I said, the additive manufacturing, the cost of manufacturing remains same, irrespective of the complexity of the design. So let's say this is cost versus complexity. So you have x-axis geometry complexity, y-axis cost. You see, in conventional manufacturing like die casting, injection molding, machining, or even you call casting. So as the complexity of the part increases, sometimes the part cannot be withdrawn from the mold. So you cannot have undercuts, you cannot have re-entrant features, and sometimes you have to give draft angles, and sometimes you have to keep the uniform wall thicknesses. And sometimes what you need to do is you need to maintain, let's say, some distance between the features, and so that it can be successfully die-cast and things like that. So essentially, we are talking about conventional manufacturing technologies, which actually becomes extremely difficult when the complexity is slightly increased. So that's why designers use a principle called KISS, which is called keep it simple, stupid. So they want to keep everything simple. So this problem is always there. Like when you take any discipline in textile, the fashion designers may want so many things, but the textile engineer may not be able to produce that. And similarly, in architectural, civil engineering and architecture, architects want no beams. They want they want to make something so beautiful without beams, but you cannot support it. So people will put beams every here and there because the structural engineers would find it extremely difficult to make it. So you have this problem there. Like someone like designers wants a lot of freedom, but the problem is there are structural aspects, there are feasibility aspects, technical feasibility aspects, viability aspects, cost issues, which may restrict people who are in shop floor, who are in manufacturing, who are builders, who are makers. So this disconnect is always there. So then the manufacturers told, why don't you keep it so simple? Like I want straight surface so that I can mill them. So if I have a very complex shape, then my tool cannot approach it. So there is a tool accessibility issues in machining. So why don't you keep it straight surface, right? So those are the things that normally people would excuse me. Yeah. So they get a complexity at the same cost in additive manufacturing because they eliminate the time. So that is why design for additive manufacturing or utilization of the additional design freedom. So what happens is like when you are able to make the same design and you make it more complex, but make it an additive, the cost remains flat. So they are getting additional advantage of cost here. Otherwise, if they would have made the same complex design in conventional manufacturing, they would have incurred a very high cost. That savings is what Industry 4.0 and industry is now, because now it has become, you would have seen this Gartner's hype curve, right? So it hit the hype curve. It was in the peak of inflated expectation at some point, and it has now reached the plateau of productivity for some applications like medical and dental, and it is now in the trough of illusionment in some aerospace applications. So, and this is a typical, you see the hype curve. So it is now exposed to, the highest peak of inflated exploitation. So many applications, so many industries are now trying to turn their attention. And many industries, commercial research groups have moved into additive manufacturing just to tap into this potential, because there's not a lot of money industry wants to put here to basically make the design more complex and make it in additive manufacturing. That is the thing that we are talking about. Now, so as I said, design for additive manufacturing, I'm going to focus my attention on design for additive manufacturing, which helps to basically achieve the I 4.0, the industry 4.0 objectives. So I'm going to focus a little bit more on design for additive manufacturing in today's lecture. And then probably I will move to general research perspectives on industry 4.2 towards the end, and then finish my lecture. So yeah, so the organizers, so could you please kindly tell me how much time I have? Maybe 30 minutes more? I think I have 30 minutes more. Yeah. Okay, so these are the tools and techniques. We have part consolidation is one of the technique where you take multiple parts and combine them into one parts to take advantage of the simplification, design simplification. And you also do lightweighting, which is where you introduce a lot of lattice structures so that you can lightweight the parts. So because in many industries they want to cut cost because the fuel cost is increasing, and there is a pressure from government to increase the fuel efficiency. So for that, if you want to make a car fuel efficient, you have to reduce its weight. So one of the lightweighting strategies is to introduce lattice structures and do structural optimization for mobility solutions, especially automotives. And heterogeneous modeling is about making multi-materials and gradient structures so that you can actually tailor some functions in different regions. And also use generative design type of principles where you can actually explore. I'm going to show you towards the end one aerospace examples of how you can use generative design. So generative design is about iterative process, which you can get an optimized design, not just one solution. Whereas in topology optimization, you also optimize the material layout for within a given design set, but you get only one solution here. Whereas you get multiple solutions, and then you can actually optimize the cost and other things based on those multiple solutions. And you can use artificial intelligence here. I will tell you about how people use deep generative networks and things like that. So generative adversarial networks. We'll just see one case study towards the end, how people use this techniques to design. And hierarchical structures is about using multiple structures in different hierarchy, like starting from macro to meso to micro to nano. So the same repeating structures, like you see in the trees, right? So the overall shape and then the leaf shape and the branches shape and the leaf shape, and within the leaf you get the same shape, right? So something like very similar to that. So you can have a hierarchical structures to get maximum strength and maximum light weighting possible. And I already told about topology optimization, which is about reducing weight by optimizing the material layout. So it means that you first do the functional design, then do the form design. In functional, you apply all the loads and things, define the function, and then optimize the material layout. So for example, where the material is sitting idle, which is not taking any stresses, which is not doing any work in that design, so just remove those materials and only keep the material where the stress flow is there, where the heat flow is there, and where the conductivity is there. So you can do many heat transfer problem and optimize. You can do a structural problem and optimize. You can also do electrical conductivity, thermal conductivity. You can also do acoustic optimization and also remove the materials where it is not doing any function, and then make foam type of structures. And the topology optimization can be solved for many different types of domains. And hybrid AM is like, so far I have been only talking about conventional versus AM. So as I am pitching conventional process over AM, because AM has advantages, right? So now what is this hybrid AM is about, instead of making them more competitive between the additive and the subtractive, so they can complement each other instead of that. So you can take the best of both worlds. As I said, additive manufacturing is good at handling complexity and good at handling variety, but it doesn't handle, let's say, accuracy really well. So because it suffers from poor accuracy, whereas machining can give reasonably good accuracy. So combine the best of both worlds. So if you are able to basically finish those things with machining, so build a near-net shape part and then build it. So also it is for material efficiency. For turbine blades and all, they take a solid material, and then there's something called buy to fly ratio. That means when you buy, let's say, 1 kg of titanium, and then maybe only you are using 100 grams of the titanium in the end part. So you are wasting 900 grams just as a chip by machining it out. So probably you can actually build, let's say, a 200 gram near-net shaped additive part and then machine only 100 gram out of it. So instead of wasting 900 grams as a chip, you can basically only 100 grams as a chip. That means you are building, let's say, a part into a near-net shape in additive manufacturing, and then you bring in the subtractive to machine out. So it brings huge savings. Titanium is extremely costly material, and aerospace industries wants to increase the buy-to-fly ratio. So buy-to-fly ratio of 1, which means that whatever parts that you buy, they always go into the flight. So, but if you're wasting a lot of materials as a chip, then that is when you have to think about building some near-net shape in AM and then machine it to finish machining. And also there are a lot of recent opportunities come where you can put multiple materials. This is not sustainable because we have been talking about the juice and Tetra Paks and other things where they combine multiple materials. Like if you take a Tetra Pak, you have metal, aluminum foil, you have paper, and also you have polymer sheets together sandwiched to create a nice packaging. But the problem is how do you, in the kabadiwala or the recyclers, how do they separate them? So that's becoming extremely important recycling issue or a sustainability issue from the viewpoint of end of life materials. But the problem here is about multiple materials is like still you can put multiple materials in one part, but again, as I said, it has got ecological challenges. But it actually helps in many cases. For example, you can lightweight, so you can make multiple material parts to basically do elastomers and plastomers, elastic plastic parts, and then metal plastic parts, and then metal ceramic parts, and metal electronic parts, things like that. So functional integration can be done to basically through part consolidation or through multi-material or through generative design or through hierarchical structure. So what is this functional integration? It means you can actually integrate many technical functions. Let's say you have mostly you have structural design, right? So then if you have also heat transfer additionally, so you can also improve the heat transfer of the cooling function where you are doing a structural design. So probably I think you would have seen the fin type of structures, right? So you can have a structure which can increase the heat transfer. So that means you are integrating that structure into the heat transfer. You don't have to have separate fins. So the fins you can make, let's say, a pot like a foam type of structure where you have the heat transfer happens by the design itself. So you can make a very complex bio-inspired design which eliminates the fin, addition of fin or heat conducting surfaces. Or maybe acoustic. I think you must have recently heard about 4D printing and other things, 4-dimensional printing, where people are trying to print acoustic metamaterials. So let's say you want to increase the, let's say, acoustic damping. So for noise and vibration and hardness, NVH, people would like to basically put a functional surface which could actually filter out the noise of certain frequencies. We call this as phononic band gap materials, right? So those kinds of things can be basically made using additive manufacturing or 3D printing. So this is about integrating as many technical functions as possible, right? So, and also we have mass customization or customize the design for personalization and flexibility. That means essentially what we are talking about here is about you customize the design for hundreds of people and at the same time make it the low cost of mass production. So that is what is mass production. So I will quickly share you a few slides. I'm not going to spend much time on this slide, but I have a summary slide where I spend a little bit of time to explain. But I'm going to show you some few cases very quickly, which is not coming from my lab. So because some of our work is still unpublished. So what I'm trying to explain you here is through some case studies I found in the web. So you can also browse through them and then you can find them in the web. So, but I have a few case studies of my own, but largely most of the case studies come from the web. So I'll just show you, share with you some of those case studies. For example, part consolidation, the first principle. So you can take multiple parts which has too many fasteners, right? So you can consolidate and make a bionic, bio-inspired design. So this is more nature-inspired and it's like more organic in shape. And also these designs are too complex, which is very difficult to manufacture in conventional manufacturing, but in additive, it becomes much easier because you are going to do. So as I said, how do additive manufacturing handles complexity? I think you have not asked this question. The problem in 3D is like most of the other processes need to be in 3D. But whereas in 3D printing, it handles geometry in 2D. So it breaks down the complexity into 2D. So because we are doing only a layer, right? So you are going to pass planes along the spots and then slice them at multiple heights and get the contours of that slice. So that means you are using a divide and conquer approach. So you take a very complex design and then you slice them. When you slice them, you get layers of 2D contours. So essentially it's just 2D printing in third dimension. So do you understand? So that is why it's, so 3D printing itself is the name is a monomer. So it's a misnomer, right? So what people can call it simply a 2D printing in third dimension. So that is what is happening with in this many additive manufacturing processes, right? So like this, you have a sheet metal parts, right? So you have to make a lot of these sheet metals and then again microweld them together using ultrasonic. So it's a painstakingly complex process. So where you can actually modify the design to make it one, and then you can make it like you can. So these are called part consolidation. In fact, we recently published a paper in a conference in ICARD 21. We make a network-based approach. I didn't present my results here. Probably next time I'll show this. So we used to identify using a network mapping the potential candidates which can be selected for part consolidation, so that you can achieve a part consolidation for a variety of different cases. So we have done a few cases with bicycle frames and frames used in aerospace structures and things like that, and fan frame used in aerospace and things. So this is about the mass customization. As I said, you have hundreds of varieties of same part. This example is a very good example to understand it. So for example, this is the hearing aid shells. People would like to basically get a customized in the canal hearing aid shell. So this would be going into the canal. So it won't be seen visibly from outside. So it becomes easier for people to wear it. So without noticing that they have a disability. So this comes in different shapes and sizes because each individual person's cavity is of different shape. But if you want to make a mold for this in conventional manufacturing, it would have been extremely costly to make these shells. So what people normally do is put a plaster of Paris or into the patient's ear. So let's say 100 patient comes to an ENT specialist. So he can make 100 different designs customized to the individual patients, and then over the night they can build in powder bed fusion, a polymer machine. So 100 designs can be nested inside that build volume, and then they can be made layer by layer at the same time. All of them are different designs. You don't have to make 100 molds for 100 designs, isn't it? So that becomes extremely cheaper. So this is what is mass customization about. So these are some niche applications. And again, this is like a surgical guide or a tooling in medicine industry. So this is actually again a drilling process. Like we use jigs and fixtures, they need to drill. The length that they need to drill and the angle that they need to drill has to be fixed. Otherwise, they may drill into the bone and also go into the alveolar nerve, which is extremely painful for the patient. So they want to limit. So this one jig can help them to basically drill the locations and also limit the depth to which they want to drill. So it's extremely, so you can plan using a CT scan and 3D print this particular surgery guide, and then you can drill the holes to fix an implant. It may be a patient who has lost his lower mandible through, let's say, cancer by chewing tobacco, or probably a trauma patient met with an accident, and then we want to basically completely fix implants, dental implants, and then maybe put a dental crown on top of it, right? So this application, like you can make hundreds of the same varieties. This comes from medicine, and also there are applications in engineering, which I have not shown because it's very difficult to justify the cost. But there are some people who would like to spend money to get the customized seats, customized parts, customized cars, customized mobile phone cases, and customized devices. So, and also you can tailor make the structures. Like you can have tailored porosities, like bone-like structures. As I said, internally you can have a very high porous structures, and outer you can have a very low porous structure, so that it mimics that like our bone. So if I look at our bone, the callus bone, so you can see that the inner regions, like the marrow regions, have extremely porous, whereas when you move to the exterior surfaces, it's extremely dense, right? So those kinds of properties you can actually model them and then print them. These are titanic forms printed. And topology optimization also, as I talked about, start with the initial design, right? So like this is a hydraulic manifold, wherein you have multiple. This is ideally used in truck. So also earth movers, like so where you want to basically move your front arm or the back arm, the bucket excavators and things like that. So you want to control many things using one single hydraulic pump. So you may have to do a routing of that hydraulic into different cylinders. So there you use hydraulic manifold. So this is typically the large weight components. Now people are talking about efficiency, so they can make from here to here. So they can move. So how do they do is they do a topology optimization. So they start with the design, eliminate the materials which are not there doing this function. So this has been designed in such a way because when people can have, let's say, a drilling machine, they can only drill straight holes. You cannot drill an inclined hole in a milling machine. So you only can drill a hole which is straight. So that means you need to have a very solid block where it doesn't have any inclined holes or curved holes. So in additive manufacturing, you can have any curved shaped holes. And also this entire block need not have to be machined. So that's the reason why you can optimize it and come to this point and it can be readily manufactured. There are some support structures which you can see. So this is the final design. So from here to here, you can say that the weight reduction is almost around 56 to 70%. So in some cases, it has even gone further. So that means you are able to basically reduce the weight of this component and then further encouraging the fuel savings. Right? So this is an exemplified case study, which is from BDT research. So the steps are like this. You start with the frame like this, and then you optimize it, right? So how do I do it? First, run a FEM simulation. You define something like a preserved geometry. So you initially design space and then apply the loads, and then it will solve an FEM problem. And then wherever your material needs to be kept, it will be kept there. Other regions material will be removed. So these are steps in topology optimization. So you can see here, initially it has got a lot of holes drilled on its surface just to do the weight savings, right? So then you de-feature, you remove those things which are already there for weight saving because you're going to do a completely different paradigm of weight savings of materials instead of just machining some regions out through milling machines. So these are some circular pockets that they were machined on the milling machine to reduce weight. But here you de-feature them and then give them as an initial design. There are some regions where the assembly has to happen. So you keep them as preserved regions. Other regions is like where it is to be optimized. So wherever the fasteners and joints, you assign the materials and loads along them, and then generate ideal shape and then smooth it off using polynubs, and then again do a FEM check to see whether it is having minimum allowable deflections with the factor of safety that you have chosen. And then finally you manufacture it. So this is extremely difficult to manufacture in conventional process, but you can additive way you can actually make them. So you can see the fasteners or connections are maintained, their geometries are preserved, but other geometries have been completely organized. And further, if you want to do weight reduction, you can also put lattice structures. So there is a software called Topology, which actually does everything for you. There's a workflow. There's a software called Autodesk Fusion 360, which generative design model it can do. Like there's a software called Inspire or Altair, which can do this. There's ANSYS also has, Siemens has. Like you have a lot of these commercial companies which can actually do these things for you. So I show you another one example, which is called generative design. In generative design, you can actually start with an initial design, but the problem here, how it differs from topology is topology, you define initial material layout. Instead, here I'm not going to define an initial material layout, but I'm going to only define the preserved geometries and also negative geometry where I don't want the material to be. In topology optimization, I'm defining where I want the material to be. Here I'm defining these are the regions which is the negative region where those are preserved regions are there, and also I define regions where I don't need my material to be put. So then, then I define my loading condition. This is an example coming from G, which is called G engine bracket. So usually I give a demonstration of the software also with the help of my scholar if it's 2 sessions, but this is being only 1 session. Today I may not be able to make an arrangement to demo the software tool. So we can do that at another time when we have, we can demonstrate the software, how it actually works. So this is the output of the design. So you can have multiple designs for the same G engine bracket, so that you can see these regions are preserved. So these are where the fasteners are. This is a G engine bracket, so where the engine is going to be mounted with this bracket. So this is the region which is typically the preserved region, or the negative region where I don't need to put the material, and this is the preserved region. Preserved parts of negative region I have defined, and then I got the results like this. So you can see multiple outputs like this. So all these things are typically called as generative design outcomes. Each of the outcomes are extremely complex. You can use their view similarities, like which look similar, and we have in fact developed an artificial intelligence-based decision support system to select one design among all the generative design. So we used to have defined different complexity metrics. Excuse me. So this becomes an extremely easy way to basically find out one design. You can also use artificial intelligence and then define some optimization weight targets and other parameters to iterate on your own and then optimize again and again and reach your target. But also you can apply some constraints. For example, in additive manufacturing, so one of the issues is like you have the support structures. So as I said, additive manufacturing doesn't need tooling, but still it needs some support structure, which can be called as a tooling in conventional sense. So what is this support structure? Suppose when you are trying to build some parts, if there are some overhangs, you need a support structure to support those overhangs. So designing them and then building them and removing them is a painstaking process. So normally one would like to avoid these kinds of process. So they need to optimize your design in such a way that your design doesn't require any support. So it optimizes surfaces which are only 45-degree angles. So steel and other materials can build up to 30-degree angle without any overhangs. Overhangs can be built without any supports, whereas in titanium it can go up to 45 degrees. So you can see that your applications could be looked at without actually building the support structures. So that's the additional constraint you can impose, cost constraint you can impose. So a lot of other things can be done. Heterogeneous objects, in a sense, would be like you have multiple properties and multiple materials at different spaces. So I think you would have heard about anisotropic. As I said, additive manufacturing is usually anisotropic. The build direction strength is always poorer than the XY direction where you're trying to build, right? So, whereas heterogeneous means it varies with position. So you can have multiple, like in this example here, it varies over the position. So the fiber content varies over the position, and also strength varies over position. So this is and also there is a smooth transition from one material to other material called functionally gradient structures. So you can use heterogeneous modeling principles to additive manufacturing. If you use 2 nozzles of materials to deliver, or 2 filaments of materials or 2 powder feeders. So what you can do is to control the flow rates of the powders and control the nozzle filament deposition rate, and then make smooth transition between one material to other material. So that could be, for that you need a CAD model to define. For example, this is a CAD area. So you have rail curves. Along the rail curves, you can actually vary the process parameter. For example, let's say I want to make this as a 2 material system in a FGM, a functionally gradient structure, which is called compositionally heterogeneous material. And I want to vary the composition here. So what I want to do is, like in the first, this material, M1 material may have, let's say, 100% copper system, and this may be 100% nickel. So 3 material systems, right? So I want to vary this from 0 from here. So along the rail curves, I can vary from 0 to 1 and parameterize those particular things. So have 0.1, 0.2, 0.3, 0.4. So I can have 10 positions across this every rail curve, and maybe I have a medial axis transform, which actually at the center, and then I can make a automatic material distribution, and I can make a functionally gradient structures. Sorry. So the hierarchical complexity is about making structures in multiple scales which are repeating. So you can say like this is a macro scale, and then the meso scale, and the micro scale, and the nanoscale. So on sub-nano and atomic and molecular level, so you repeat the same structure so that it actually has superior performance and properties. So you can do them in multiple ways. You start with, let's say, design repeating structures. So you start with the octahedron, then octahedron of octets, an octet of octahedron, then octets of octets. So like that, you can repeat them in multiple scales. You say 0th order, 1st order, 2nd order, 3rd order. You can get multiple structures. These complex structures can be very easily manufactured in additive manufacturing. Or else you can also use the same hierarchical structure by using, let's say, rotation and mirror or fractal cut. So you can use these methods. They are available commercially now. And as I said, multiple material systems, like you have composition of nickel. You want to have nickel 100% here at one place, right at the 11th position at the outer side, and copper 100% at the center. So it's a copper nickel system. So you can actually have variation in, let's say, the composition across the radius of this. So you can make such a functionally gradient structures and multiple materials within that additive manufacturing. And functional complexity is all about, getting your multiple functions like structural, thermal, fluid, flame retardance, and then electronic, IoT. So all those things can be done here, right? So, sir, just to, I'm in a classroom, so I'll just call you back, sir. Okay, Okay, so that is the way forward, right? So you have to basically combine multiple functions. So let's say in topology optimization, I want to have a conformal cooling channel to increase the cooling performance. So rather drilling process only allows straight channels, right? So you can have conformal cooling channels, which could help you to basically, reduce the weight of the part and volume of the part. So 19.2 kg to 1.2 kg. So footprint from 210 to 85. And total volume from 2,900 to 2,244. So you can see the 10 drastic reductions. That is why industry is much more interested. And also you can put multiple properties, like property like flame retardance and shock absorbing, or sometime impact, sometime, so multiple functions in multiple regions, and you can embed them together, lubrications and things like that. So this is functional integration. So earlier, this is the forged or a cast part. People would have normally machined it for weight savings, and this is what they do. But here you can topologically optimize the design and also put lattice structures, and also add functional materials like, antennas. For IoT, let's say you have a turbine blade, right? So you want to measure the pressure. So what you want to do is you want to print 2 things on that sensor. In fact, 3 things. What do you want to print? So you want to print a button. You want to print an antenna. You want to print a RFID antenna. You want to print a sensor which senses the pressure, and you want to also print an energy supplying device. So now either you can print the batteries directly onto the surface in functional integration. Otherwise, what you can do is like you can have a RF energy harvester printed on it. So you have 2 RF antennas. One antenna receives an RF energy from an RF source, which is next to it. Like you have this FASTag, right? In the FASTag, you use the RFID tag, right? So it receives energy, harvests the energy from the transmitter, and sends the data back through another receiver, right? So very similarly, you can have an antenna which can be printed on the part. So it harvests the energy initially from one of the transmitters, the low power RF, high power RF, and then you have a low power RF which sends the data back whatever data you sensed, the pressure. So you have a sensing element, like you have wearable strain gauges, right? So you would have seen them. They measure your things. So you have a lot of wearable devices which have come, which are flexible electronics, wearable electronics. So those things are typically printed, like, so they can be printed on the functional part. So you add another functionality, the IoT functionality. IoT is all about this. What is IoT? In vehicular or transportation, in healthcare, in manufacturing, it's all about instrumenting sensors and collecting data and then transmitting to a network through an antenna using any one of the machine-to-machine communication platform, and then you are analyzing the data over the cloud. So that can be done by embedding this function, integrating them into the same part where you are trying to 3D print. So let's say you assume that you have a car, right? So on the roof you print the photovoltaic cells, on the bottom you print the micro batteries, and also the bus bars and interconnects, everything can be 3D printed. So you have a top of the roof which takes the solar energy and then puts in at the bottom of the roof. So you don't have any batteries at the bottom like Tesla's have. So Tesla is trying to build flow batteries and even micro batteries and then photovoltaic cells, so that the entire vehicle paradigm gets changed. So that's the reason 3D printing can do all these things. But it's very nascent stage. A lot of universities are researching around this topic. So this is a summary. It's a very busy slide. I try to explain this what it means. So we have the form complexity, we have an hierarchical complexity, we have a functional complexity, and also you have a material complexity. I discussed about geometry complexity. I told them, you can have walls and ribs need not be there. Wall thicknesses combination can be used because in conventional injection molding, so what happens is that when you use multiple thickness combinations, thin sections cools faster than thick sections, causing warpage, differential cooling, right? So, and people try to make uniform thicknesses. So that can be avoided in additive manufacturing. You can have free-form surfaces having very large aspect ratios, undercuts, which becomes extremely difficult in conventional process can be possible. Small gaps between features is possible. Big cross-sectional changes is possible. So no draft angles. Otherwise, in casting and other things, you have to provide draft allowances, which is in injection molding also, because the part has to be taken out of the mold, right? So, and hierarchical, as I said, you can have multiple hierarchical structures like mesoscopic lattice structures and honeycombs, and irregular porous structures, like you can have tailored porous structures and things. In material complexity, you can have material transitions and different materials in one part. That is also possible, isn't it? So you have functional complexity. As I said, you can have multiple parts consolidated into one through part consolidation. You can embed foreign components like electronic components, like active, passive components, sensors, and antennas and batteries, and extend the functionality of an existing component. Like you can take a simple foam type of structure, and then you can have foam type of structure which can actually absorb the impact on one end, and you also have a structural solid on another end. So both things can be combined into one part. And or maybe a noise suppression, or maybe acoustic suppression, and also eliminating the reduced materials and consumption. So you have a lot of exemplary benefits out of it, like reduction of design space, isolation, like as I said, isolation from sound, isolation, improvement heat transfer, conformal cooling channels, energy absorption, impact, damping, as I said, vibration. You can actually make structures which is more damp. Reliability, because you improve the quality. Aesthetics, very complex shapes, lattice structures, weight reduction, and it is easy to hold. Ergonomics, like organic structures. Outer flow dynamics, like it's aerodynamic, very free flow structures. High energy efficiency and conversion and transport. So because of the energy efficiency, right? So inner flow dynamics, especially with complex cooling channels and things. So you can see exemplary benefits. And cost, you can see like many costs gets reduced, and also the sustainability gets improved also. So these are the value proposition that you get in design for additive manufacturing. Okay, so I'm just take 2 minutes to explain you a case study. So how DFAM can be done. So as I said, we have functional, economical, and requirements. If somebody wants to move to AAM, they have to check the AAM suitability, and if they see an opportunity, then they can go ahead. Otherwise, they can go to the classical design and production process. So they can define an AAM process, and then they can do the requirements to materials and process. They can do initial cost benefit analysis, and then if it's economical, they can go to topology optimization, generative design, lattice structures, right? Or they can go for hierarchical structures for internal geometry for functional purposes at macro level or micro level, then porosities and all those things. They can put multiple materials and material gradient structure, FGMs and things, or else they can eliminate the AAM assemblies and consolidate the parts together. So they get a lightweight products, surface modified products, internal geometry modified products, and aesthetic gradient products and functional assemblies. And then they can build, define the build parameters, AM related constraints, like as I said about support structures and the constraints in processes, and then process constraints like surface enhancements and inspection, and then optimize, and then they go for final production. So I'll just show this is the enablers. As I said, you can do individualization, improve the aesthetics, functional integration, thermodynamic behavior, mass reduction, right? So mechanical behavior. Also have simplified manufacturing process and faster development, right? So you have a lot of objectives and improvements there. So I'll just give you a very simple 2-minute case study of how you can use something like a deep generative design framework by using deep learning algorithms to basically iterate many designs. For example, you gather a lot of previous designs and generate the new designs by topology optimization, and then filter very similar designs. As I said, we use view similarity algorithms. We recently published a journal in the AM journal which talks about view similarity based algorithms. So we used techniques such as artificial intelligence techniques to understand the similarity of different views, and then generate new designs and filter the similar designs and evaluate the design options. So how do we do that? Let's say, I think I'm missing some slides anyway. So I'm missing a few slides, I think, anyway. So I will stop at this point. So before I stop, I will tell you about the research gap. So what are the research gap, especially about Industry 4.0, not just related to 3D printing. In 3D printing, we have, as I said, all these topics, very active research is going on right now. In what is Industry 4.0 is about complete autonomy and automation, right? So we have digitalization, which is about CAD and islands of automation. And then communication and standardization is about making parts interchangeable, and then having more CAD standards and part standards for exchange of information. Flexibility is about variety flexibility, volume flexibility, customization, that's we also talked about. And real-time response is what I talked about, the agility and the ability to handle critical orders. And maintenance predicament, these are manufacturing concepts. And these are the several manufacturing philosophies or systems, like single station, automated assemblies. Like I have shown the plants, many plants, like single station automated cell is about having one cell where everything is happening. As automated assembly is like the moving assembly lines. Flexible is like more batch type of production rather than mass or job, right? So FMS types and seam systems, which is again use a lot of material handling, automated material handling and things. Reconfigurable is where the dies are eliminated by reconfigurable tooling and things like that. So there it can actually have a very higher degrees of this thing. So whereas if I look at predictive maintenance and other things, is what Industry 4.0 is the immediate target. So this is the gap that people identify. For single cell, customization is the target. For automated cell, the gap is standardization. For flexible, it is about real-time response. For SIM, it is about flexibility, right? So for reconfigurable system, it's about predictive maintenance. So these are the immediate gaps that people identified and they are working on Industry 4.0. But ultimately, this is the vision for Industry 4.0. The lower is context-aware and context-sensitive and self-configuring and self-aware systems. These are the things that people want to do research and push every systems into that. So I want to acknowledge my team. So these are my students, research students and masters and students in my lab who have been contributing to my research. I have not presented much of their work here because many of them are still under publishing and copyright issues. So I took, which is generally available so that we can put it in YouTube and other places. Because we have a lot of published work which we cannot put in YouTube because AICT ATAL recordings are usually put on YouTube. There are conflict that is available. So I took materials which are freely distributable and then I put them. So anyway, I'll share with them, and we have face-to-face, in-person training programs. I'll share much of those materials. Right? So thanks for this 3D printing I 4.0 webinar. If you have any questions, I don't know what is the mechanism. This platform is extremely new to me. So maybe the organizers can come in and then probably we can arrange a few Q&A sessions if possible, if time permits, otherwise it's okay. Thank you, sir.
Yes, sir, thank you so much. Thank you so much for your excellent lecture. And so participants, those who want to clarify your doubts, you can post your questions in the chat box. Else you can raise your hands. I will allow you to come and ask the doubts in the straight away the next time. So you can post your questions in the chat box, or you can raise your hands so that I will allow you to come and interact in online. Sir, thank you, sir. No questions has been asked.
Okay, I think it is well understood by everyone.
Yes.
So
Thank you, sir. Thank you so much. We will.
Okay, so you can always
Thank you.
reach me. I have my mail ID. So I have my mail ID here. So if you have any questions, if you feel hesitant to ask in front of all the participants, you can send your questions and queries to this mail ID. So thank you all for your patience.